So last time we introduced the topic of a composition series, and so let's do some more examples. I also talked about some more different definitions at the end there that I didn't really have a chance to go into more details on. More specifically, talking about different groups having, or rather having different composition series which are equivalent. And I made a point to mention that the groups don't need to be the same. So let's take an example. Oh, that's much better. So we take Z4 containing Z2 containing E and Z2 cross Z2 containing Z2 containing E. So let's see here. Oh, by the way, by Z4 I mean Z mod 4Z. I don't want to write out the whole thing every single time, so I'm just going to stick with this. So we have two composition series here. Are these composition series? If you take Z2, so Z4, that's 0, 1, 2, 3. And then you can think of Z2 as a subgroup by just the element 0 and 2. And then I think you can just check directly that these are normal subgroups. Oh wait, no, of course, because these are abelian groups. All of these are abelian. And so because they're abelian, you can just move things around, and so yeah, it's everything's going to be normal, and so that's fine. So what about the graded pieces? Well, if we look at this graded piece here, we have Z4 mod Z2. Well, let's see here. What's going to be the size of that? Well, the size of Z4 mod Z2 is going to be 4 divided by 2, which is just 2. So Z4 mod Z2 is isomorphic to Z2. And obviously Z2 mod the identity is just Z2. Similarly here, Z2 mod the identity is Z2, and Z2 cross Z2 mod Z2, well, the order of the quotient is going to be the order of this divided by the order of this, so 4 divided by 2, which is 2. And so every single graded piece is Z2, and so in particular they're all isomorphic to each other. And so for that map that we had where you rearrange the graded pieces if necessary, we don't even have to do that here, because this quotient is the same as this and this quotient is the same as this. And so therefore, these, here, I want to rewrite this example because that's bugging me. There we go. Okay, so these composition series are equivalent even though Z4 is not isomorphic to Z2 squared, which by this I mean Z2 cross Z2. And obviously they're not. Z4 has an element of order 4, Z2 cross Z2 has all of its elements are order 2. So yeah, you can have situations where even the groups themselves don't have to be the same, like Z4 and Z2 mod Z2 are completely different groups, but the composition series end up being equivalent. So there we go with that. And so you might think, okay, well, what's the use of having equivalent having this definition. If you can have two composition series which are equivalent even though the underlying groups are. It appears that this is sort of a weak enough condition that we can actually do things that are interesting. And so here's an example of something that's interesting. So this is a theorem. This is the Schreier Refinement Theorem. So I think it's Schreier. That might be how you spell it. I don't know. I feel like Jack Black trying to spell Mr. Schneebly. So this is going to be the Schreier Refinement Theorem, and it says that any two composition series, let's say sigma and sigma prime, have equivalent refinements. Say sigma 1 prime. No. Here, and sigma 2 prime. Okay, so I don't want to call these sigma and sigma prime. I want to call them sigma 1 and sigma 2. Okay, so what does this mean? This means that we have two refinements, sigma 1 and sigma 2, sigma 1 prime and sigma 2 prime, such that sigma 1 prime is finer than sigma 1 and sigma 2 prime is finer than sigma 2. And also sigma 1 is, sigma 1 prime is equivalent to sigma 2 prime. So in that you can sort of see, when I say a refinement, I mean a composition series which is finer than the given one. So a refinement of sigma 1, I'm referring to just some composition series which is finer than sigma 1. Okay? So, proof. First thing, let's give these things a little more detail. So let sigma 1 be G, and then so this is going to be of G. So two composition series of the same group. Okay, so I guess this doesn't really answer my preamble of like addressing this whole thing having two different groups having equivalent refinements, but whatever. So anyways, now we're going to have this be H naught through Hn, which is the identity, and then sigma 2, which is G, this we're going to call K naught through Kp equals E. And this P here is just an example of us struggling to find good letters to use. It's not prime or anything. It's just some letter that's not N. Why don't we use M? Let's use M. I'm really going to regret this if I end up making mistakes for not remembering to replace all instances of P with M. But I don't see any reason not to use M here. Okay, so here's what we're going to do. We're going to use each refinement. We're going to use each composition series to refine. Basically what we're going to do is we're going to take like sigma 1 and we're going to use this to put like a composition series of this size in between every single inclusion here. And we're going to do likewise. So we're going to end up with like a whole bunch of repetition. Or, well, not repetition, but these refinements are going to be quite larger than the originals. Okay? So let's write that out. Use sigma 2 to insert m minus 1 terms between those of E2, E1 to obtain sigma 2 prime. Obtain sigma 1 prime similarly. So what we'll do is we'll insert n minus 1 terms between each pair of terms in sigma 2. No. Right? Use sigma 2, right, to obtain, no, this should be sigma 1 prime. So we start with sigma 1, and we use sigma 2 to insert terms between those in sigma 1 to get sigma 1 prime, which is obviously going to be finer. And then obtain sigma 2 prime similarly, meaning that you start with sigma 2, and then for each inclusion in sigma 2, you insert n minus 1 terms in the middle there using sigma 1. And I'm going to go into detail on how to do that. We will show that sigma 1 prime is equivalent to sigma 2 prime. I'm just going to write that to mean equivalent. I don't know if this is an equivalence relation, so let's write this, because we haven't given any specific meaning to this symbol yet. So let's say, oh, this means that these two composition series are equivalent. Okay, so here's how we're going to do this. So we're going to define Hij prime to be Hi plus 1, Hi intersect Kj, and Kji prime to be Kj plus 1 times Hi intersect Kj. So then we have Hi is equal to Hi0 prime, right? Why is this true? This is true because, so your Hi0 prime is just Hi1, no, Hi0 prime is just Hi times this, and this is going to be H0 intersect K0. Well, what's K0? K0 is G, so this is just H0, and H0 is Z, or G. So this is going to be Hi times G, but Hi is a subgroup of G, and so Hi times G is just going to be Hi. And that's exactly what we have here. So there we go. So this is going to contain I1 prime, and that's just because when we go from I0 to I1, what increases? This Kj goes from K0 to K1, and K0 contains K1, so we're intersecting by a smaller, right, we're intersecting by a smaller set, and so it's going to get smaller. And so this is the correct containment, and then this is going to go all the way down to Him prime, which is equal to Hi plus 1. and is this obvious. So hi plus 1, or rather hi prime, so we're going to get hi plus 1 here, and here we're going to get hi, and we're going to intersect with km, and km is e. Oh, so this is just this times e, and so that's just this, which is this. And so there we go. So this is how we insert, and how many terms do we have here? We have 0 through m. Right, so how many terms are we inserting? We're inserting, let's see here, 0 through m, that gives us m plus 1, but hi plus 1 and hi were already there. And so we're inserting m minus 1 terms. Okay, so that's how we're inserting m minus 1 terms between those of sigma 1. Because we take every hi containing hi plus 1, which is these two, and we just throw in all of these. And so that's how we do it. All right. So, and we do the same thing for kj. I'll just write it out, but you can check by the same, you basically do the same argument that I just did. And you get this. So you get n minus 1 new terms between kj and kj plus 1. And you do this for every single I and j between, I don't know, whatever ranges of I and j you have to do them to make it make sense. Okay? So we need to prove what? We need to prove that hi comma j plus 1 prime is normal in hi j prime, and we need to prove k j comma I plus 1 prime is normal in k j I plus 1 prime. Okay, and why is this? That's exactly what we need to prove that these containments are actually normal, because we need all of these containments to be normal in order for this to be a composition series. Okay, so after that, we're not done. That once we prove this, then we'll have these two composition series, and so that's all fine and good, but just because you have two composition series, that doesn't mean they're equivalent. What you need is you need the relation between the graded pieces, and we're not going to reorder anything, so that's really nice, but we have to prove this quotient thingy, so we need to say that the graded pieces are all equivalent. What we need is we need ij prime mod, or hij prime mod hij plus 1 prime to be isomorphic to kj comma I prime mod kj I plus 1 prime. Okay? And so if we have that, then all of the graded pieces in this composition series are going to be, well, I think there might be a little bit of reordering because you have to go from ij to ji here, but it doesn't really matter. What you're going to get in the end is you're going to get all of the, for every single graded piece in sigma 1 prime, you're going to get an isomorphic graded piece in sigma 2 prime. And the relation between these graded pieces is going to be bijective. And so what that's going to give us is that's exactly what we need for this to be a composition, or for these composition series to be equivalent, is we need that relation between the graded pieces. We also need them to have the same number of terms, but that's obvious because if we insert, let's see here, we insert m minus 1 terms in n minus 1 places. That's going to give us, here, I wrote it down. both sigma 1 prime and sigma 2 prime are going to have n times m plus 1 terms. And you can just check that on your own. The number of terms in each of those is going to be n times m plus 1. And so there we go. So what we're going to do is we're going to prove a lemma next time that tells us that for whenever we have everything that these h's and k's satisfy, then we have this normality, and this isomorphism. And that is going to be the Zassenhaus butterfly lemma, I think it's called. Zassenhaus, is that how you say it? But in any case, the lemma that we prove in next video is going to prove these facts, and then from there, we're done with the Schreier Refinement Theorem. And so there we go.